name is Alejandro, and welcome back for day 18 of me doing the Advent of Code December 2024 challenge. So today we get the problem, RAM Run. You and the historians look a lot more pixelated than you remember. You're inside a computer at the North Pole. Just as you're about to check out your surrounding, a program runs up to you. This region of memory isn't safe. The user misunderstood what a push-down automaton is, and their algorithm is pushing whole bytes down on top of us. Run! The algorithm is fast. It's going to cause a byte to fall into your memory space once every nanosecond. Fortunately, you're faster, and by quickly scanning the algorithm, you create a list of which bytes will fall, your puzzle input, in the order they'll land in your memory space. Your memory space is a two-dimensional grid with coordinates that range from 0 to 70, both horizontally and vertically. However, for the sake of example, you suppose you're on a smaller grid with coordinates that range from 0 to 6 at the following list of incoming byte positions. 5, 4, 4, okay. On a smaller grid that range from 0 to 6, okay. Each byte position is given as an XY coordinate, where X is the distance from the left edge of your memory space, and Y is the distance from the top edge of the memory space. Okay, so the XY coordinate of a incoming byte, okay. You and the historians are currently in the top left corner of the memory space, 0, 0, and need to reach the exit in the bottom right corner. Okay, at 70, 70 in your memory space, but 6, 6 in this example. So you need to avoid them, so what, they're going to be like moving or something. At 0, 0, and need to reach the exit in the bottom right corner. 70, 70, but 6, 6, yeah, you'll need to simulate the falling bytes to plan out where it will be safe to run. For now, simulate just the first few bytes falling into your memory space. Oh, so it's going to like fall and then like come back up or something like this. And you have to figure out if it's, oh gosh, that's going to be, so it's like every single, oh gosh. Okay, let's just keep reading. As bytes fall into your memory space, they make that coordinate corrupted. Corrupted memory coordinates cannot be entered by you or the historians, so you'll need to plan your route carefully. You also cannot leave the boundaries of the memory space. Your only hope is to reach the exit. In the above example, if you were to draw the memory space after the first 12 bytes have fallen, using dot and this for corrupted, it would look like this. First 12 bytes, so it's like here you have 5 and 4. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4. So this is the very beginning one, right? Up, down, left, or right. After just 12 bytes have corrupted locations in your memory space, wait, but you didn't move it? Simulate the first kilobyte. Wait, it doesn't keep... What is the minimum number of steps needed to reach the exit? Okay, let's get our puzzle input. I think I'm reading this wrong. I'm reading this, oh my gosh. Holy crap, that is a lot of coordinates. Okay. There's only up to 70 to 70 total coordinates, right? Let me calculate what that number is. So here, let's do the usual thing of, we open up that beautiful Visual Studio Code. We get rid of this part day 17, that stale stuff now. Now we're on to the beautiful, wonderful day 18. And from day 18 here, we're going to do data.txt, where we're going to slap these coordinates right into place, 3,450. Oh boy, okay. Here we're going to do test data.txt. Here we're going to do a little part1.py. And here we're going to do file name is equal to, well, first we need use test data. It's going to be data.txt, and we need a / in there. If not used equals true. If not used test data, else / test data.txt. With open file name in read mode as that's not what I want. Every single time I open VS Code, it asks me for that. Jeez. Lines equals line dot strip dot split on the comma for line in file dot read lines. Map int and list of this for line print f string lines equal. Whoops. Here we'll do CD18. Python 3, part 1, .py. Beautiful. Oh yeah, we don't have test data, right? So here, you know what? Let me just do a little fancy right there. It's kind of annoying. Oh yeah. Lambda pair int pair of 0 int pair of 1. Right. Okay, we'll just do this for now. We'll make our life simple. We'll just say that lines is equal to this. Let's print them for now. Right? So essentially, then yeah. For I in range length of lines, x comma y, lines of I equals, here we'll do a tuple with int of x, int of y. Right, that's essentially what I'm trying to achieve, and there we go. Right, so now we have the tuple xy coordinates exactly as we want them, ladies and gentlemen. There we go. The only annoying thing is that they give it to you in the annoying order, right? So here's like if I do 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4. Well, maybe they don't, right? No, the very first one is how far away from the left wall you are. So yeah, they give it to you in the annoying order. Okay. Simulate the first kilobyte. Here we'll do it backwards. Right, there we go. Okay, I'm confused. I'm confused because here they're drawing just the exact same things, right? After the first 12 bytes have fallen. So they just, so here, how many, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So just saying these 12 bytes, you just make them obstacles, that's it? Bruh. What? So you're going to ignore a lot of the input? I'm confused. I must be missing something here. I mean, okay, let's do what I think they're saying. Right, I'm going to grab this point right over here. Here we're going to make this a beautiful, beautiful true. All right. Here we're going to say num obstacles equals, or num bytes equals 12 if use test data, else 1024. Right? And passing inputs. Start passing inputs. Right, and here we'll do our beautiful, beautiful, and check this guy, and check this guy, and check this guy, and check this guy. There we go. Bada bing, bada boom. Okay, so now we've got our lines nice and ready. Okay, just like the ready opening. Okay. Okay, I'm just gonna. Okay, well, I'll be proven wrong if anything, but it seems like here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It seems like they're just grabbing the first 12 bytes, ignoring the other parts of the input. Okay, I mean, don't mind me, that makes the problem easy. As long as I understand correctly. Okay, moving that guy. So, we'll say, hey, for I in range num_bytes, here we'll do, or obstacles equals set of lines up to num_bytes. Print f-string obstacles equals set with 2460 in there. Yeah, okay. Simple enough. And then here we're going to do our typical, oh boy, directions. Here we'll do right, down, left, up. Right is equal to what? Right is equal to, we're going to go, I made the coordinates the non-annoying way, just for myself. Right, the board is 70 by 70, so it doesn't even matter, right? Or 6 by 6. I might have to undo it that later on, but here right is essentially 0, 1. This is 1, 0. Left is 0, -1, and up is -1, 0. All right. Here we'll say directions is equal to exactly these guys. There we go. Beautiful stuff. Beautiful stuff right there. Right, and so here what do? We just do some search. So here we'll do fringe. Here we'll do BFS is equal to collections. From collections, import my deck. There we go, my deck. Here we'll start off with position. What do we want? 0, 0. Do we want to do BFS or UCS? Every single action has a cost of 1. Yeah, minimum number of steps. So we can get away with BFS. Absolutely beautiful. Since each edge has same cost of 1. Right, and here we'll do cos, x, y, right? And so here we'll just have 0, 0, and 0, right? And so while length of fringe greater than 0, here we'll do cast x and y equals fringe dot pop left. There we go. Then what do we want to do? For dx, dy, if x, y invisited, and then here we're going to continue. Otherwise, we're going to do visited that add x, y. Here we'll do return x, y and obstacles. Here we'll do a visited set, right? For dx in directions, we're gonna say new x, new y, x plus dx, y plus dy. Here we're gonna say, hey, if new x, comma new y, visited and not is obstacle, new x, comma new y. Then here we'll do fringe.append a cos plus 1, that new x, and that new y, right? And here we'll say, and visited.add, that new x, new y prematurely. And here we'll say, goal state equals, so this is 0, 1, 2, 3, 4, 5, 6. Print f-string goal state equals. Right here we'll do f equals goal state f-string answer equals cost and exit the program. Raise exception, unreachable code. Right? Okay, so this is just typical BFS. Let's give it a run. Goal state 24-1. That is definitely not what I want. Yeah, I don't want this. I want 0, 1, 2, 3, 4, 5, 6. 6 if use test data, else. There we go. Right, it's a 7x7 board. Okay. Yep, so I have all 4 directions. Interesting. 0, 0, 0. Okay, maybe I should stop putting the visit thing in there, right? Okay. I need to revisit the way that I write BFS and so on. I thought it's like, I guess like, you know, I've technically not explored a node, so it's like, you know, I won't add it as visited yet. It's still kind of annoying. Right, because at least with UCS, it's like, yeah, whenever you see a node, you can assume it's like, okay, well it's just interesting, right? Okay. Yeah, okay. But yeah, here we get an answer of 22 steps, which is exactly what they wanted. Okay, this is just a strange problem, right? So here I can just print this guy out here. We'll get rid of this guy, check this guy. Right, so answer is 22. This feels like too good to, well, I mean, it's part 1, right? So let's just do this. Let's submit. And that's the right answer. Okay, you're 1 gold star closer to finding the chief historian. Continue part 2. Okay, let's see what abomination is waiting for us in part 2. All right, part 2. The historians aren't as used to moving around in this pixelated universe as you are. You're afraid they're not going to be fast enough to make it to the exit before the path is completely blocked. To determine how fast everyone needs to go, you need to determine the first byte that will cut off the path to the exit. In the above example, after one falls, there's still a path to the exit, right? However, after adding the very next byte at 6-1, there's no longer a path to the exit. I see. Can't I just binary search my way through this thing? So this example, the coordinates of the first byte that prevents the exit from being reachable are 6, 1. Right? Simulate more of the bytes that are about to corrupt your memory space. What are the coordinates of the first byte that will prevent the exit from being reachable from your starting position? Provide the answer as 2 integers separated by a comma with no characters. Wait, when I choose one, that means I need to keep everything before it, right? The 1, 1, right? Right, so can't I just binary search for my answer? The point is like, the exit won't be blocked and blocked and blocked. And then at some point it's like, oh, it will be blocked, and then it's like always blocked, right? So I can just like, what do I want? The first byte that will prevent, right? So I want leftmost binary search, right? So it's like, so it'll be a bunch of falses in terms of false it doesn't block, false it doesn't block, false it doesn't block. Then it's like true it does block, true it does block, true it does block, true it does block. And so I essentially want the leftmost one, right? So I could just do leftmost binary search. Right, so the worst case is like, 0 bytes and I'm stuck, or none bytes is all of them, right? So here it's like essentially I can take my part 1 code. Okay, this is not going to be that bad. This is not going to be that bad. Use test data is equal to false. From collections import deck. Yeah, we can, okay, we can do a little bit of whoops. Boop. Yeah, add that just because that was instructive. I need to review my BFS a little bit. Okay, so my part 1 looks a little bit cleaner. Let's put that into part 2. And so yeah, num bytes is equal to that. Def BFS. Num bytes, right, is equal to set of line of num bytes, right, and there we go. Now instead of exit, this will return cost, right? So here if I do print f string, answer equals BFS of num bytes, right? So here if I do that, and I do part2.py, I get the same exact answer. Very nice stuff, right? And if I put this as true, then I get the same thing. Essentially, I need to do leftmost binary search, right? So here what I need to do now, just do leftmost binary search. Essentially, you can have at least minimum 0 bytes fallen, and at maximum length of lines bytes fallen. At the beginning, path won't be blocked, and as you keep adding bytes, path will still not be blocked, right? Here return true. There is a path. Otherwise, while length is this, here we'll do return false. There is no path. Potentially be blocked, and therefore subsequent is the path will still be blocked. So we can treat these as booleans where Yeah, okay, the point is get, right? So here we just do L comma R. 0 comma length of lines, right? So here we'll say while L less than or equal to R, we'll do mid is equal to L plus R over 2. If BFS of mid, right, there is still a path if it's not the case that BFS of mid or exists path. Does path exist? No path as we want. Date our current result. Res. Was R at the very beginning, right? Yeah, wait. Let me think about this. We want the leftmost, right? We have a bunch of falses followed by a bunch of trues. So we want the coordinates of the first byte that will prevent being reachable, right? So there is no path, right? If there is no path, that's good, right? So res is equal to min of res comma mid. And then we check for earlier indices to see if there's an even earlier solution, i.e. set R to mid minus 1. R is equal to mid minus 1, else is equal to mid plus 1. Print f string. Here it's giving me 0, 1. And this is supposed to be 6, 1, right? Whoopsie. Alright, here we'll do f string. For I in range lines, we'll say f string equals path of I. Wait, this doesn't make sense. Oh, there is no path, right? So essentially I have it the reverse way. Wait. Essentially we want the very first false, right? Index equals. Right, if I put false for this, yeah, it's gonna be too many, right? Yeah, that's fine. Right. Although, wait. Are you telling me I can just do this linearly? Because now, essentially, I know that the answer is this guy. Right? I know that the answer is 2893. Right? If I try this guy, that's not the right answer. Oh, okay, wait, I'm being dumb. Oh, no, I need to give the coordinates. Oh my gosh, I'm so stupid. I'm so stupid. I'm so stupid. If you're stuck, make sure that you're using the full input data. Return to day 18. Yeah. Oh my gosh, I need to do the coordinates of this guy. So, oh my gosh. Yeah, here, F string, you know, lines of index, this guy. Right, and so this is the answer for this guy. Right, so I think with a comma, so yeah, I think this is the answer and so on. But yeah, let's try to confirm it via leftmost binary search, right? That's kind of the point. So essentially I have a bunch of truths followed by a bunch of falses. I want the leftmost false, right? So if this is equal to false, right, then I want to do index is equal to min of this. Okay. I got that. So why did this not work? What? Wait. Oh, I want it backwards, right? But also I'm doing 0, 1. What? Oh, wait, so I want this guy. Why is it that guy? So yeah, I have to return it backwards. So yeah, this is not going to be the answer. So yeah, so let's not be stupid here, right? So yes, this guy backwards, which is the very last true, which is fine. Oh, why would it be the last true, right? So here I'm doing. Oh, because I need to include that index. Yeah. Oh. Yeah, so that gives me the number of bytes. Num bytes equals this. Yeah. So here we'll do index is equal to num bytes needed minus 1. That's why, right? And here we'll do print f string answer line index backwards since we reversed all XY pairs for convenience inside the input parsing. Right, so now if I do something like, yeah, so now I have 6, 1 as my answer. Right, exactly as they want it. There we go. There we go. There we go. But yeah, we did. Okay, so leftmost binary search was actually kind of overkill. We can just do it linearly because we actually have enough computational power to do that. Day 18 is kind of a miss, right? Unless I missed something, but I think I pretty much got it, right? Right here we can just put, you know, false. Right, and here it's like, you know, this is my answer right here, 4516. And we can kind of confirm it because, like, you know, there's not all that many test cases. This is actually hilarious. So yeah, the point is that we have a bunch of truths, and at some point we'll have a false, and so on. They should have made the grid way bigger. That way you're like forced to use leftmost binary search, right? But here it's like we can kind of double check our work. You know, go up until we find a true here. And yeah. Essentially we want this guy, right? Is that what we got? 4516? Let me print what I got. Yeah, 4516. So yeah, let's get rid of this. Right? Let's put 4516. That's the right answer. You're one gold star closer to finding the chief historian. You have completed day 18. You can share this victory or return to your advent calendar. Wait, oh, and look, oh, okay, AOC 10 years. It is their 10-year anniversary. That makes a lot of sense. Wait, day 18 was so chill. Day 18 was so easy. I'm so shocked. That was fun, right? Instead of the nightmare we've been dealing with. Day 18 was a freebie. I'm like so shocked. I'll generally be honest. Like my goal was like, you know, I gotta get through these advents of codes and so on. So right now it's like, you know, past midnight, where I am right now. And I was like, okay, you know, I'm going to do part 1 and so on. And then, you know, I'll go to bed so that I can think about it and so on. And then come back the next day and blah, blah, blah. Just because it's like I need to be like doing these because like these last few problems have been killing me lately. And so like, you know, my entire goal was like, you know, just finish part 1 for tonight, give an attempt for part 2 and then, you know, go to bed and come back the next day and so on. But day 18 was kind of trivial. Okay, I mean, it's like I'm so stunned. Okay, and we didn't even have to do leftmost binary search. I just picked that up instantly, right? Because I was like, oh wait, we're gonna be able to do it this way. You're straight up just able to just simulate every single number of bytes, literally. I see. I mean, I won't complain. It's just, dang. Right, I would have thought like, you know, at least surely they would have made it so like, you know, it's too computationally exhausted to do that. So it's like, you know, leftmost binary search, kind of a clever trick, but yeah, it's not even needed. Right, it's obviously like, you know, that takes like, you know, good 10, 20, 30 seconds to run. Now obviously it's like, you know, just there you go, super fast. Because, you know, with leftmost binary search it's obviously a lot faster because I can minimize the number of calls where it's like, you know, I actually do a full search. But yeah. I don't know. Interesting. Okay, so you know, as always in these videos, whenever we solve one of these problems, we'll get to eat you know, our advent chocolate. I ran out of Ferrero Rochers, but thankfully I now have these German mini bears. So here I'll put them up in front of the camera here, which I'll be eating now for my chocolates for the rest of these guys. So okay, a serving size is 6. For calories of 170, so they're not 170 calories each, so this is nice. So we'll unwrap this bad boy right up, and let's open this guy. So now we have these beautiful little chocolate bears that we're gonna get to eat for the rest of the Advent of Code challenge. It's gonna be very nice. So okay, so let's grab one of these guys. And as always, I encourage you to join me for eating a chocolate alongside with me. So if you're having a chocolate alongside with me, then cheers to you, my friend, and let's go. It's definitely very rich. Oh, it tastes exactly like an advent calendar chocolate. That's actually really nice. It's rich. It definitely doesn't have, you know, the hazelnut or the Ferrero Rocher, but that's not the point. In terms of its own chocolate, that's actually really delicious. Okay. That's a good one. Okay. But nevertheless, as always, in all my videos, I do a quick recap if I was able to solve the problems. For this one, it was rather simple. Essentially, you're given a list of falling bytes. You can think of these guys as obstacles, and you know their xy coordinate. And essentially, it's like they give you a number, which is the number of these obstacles to consider. So for example, if they give you 12, or if they give you the number 5, you only consider the very first 5 obstacles. That's it, right? Otherwise, you're in a 6x6 or 70x70 grid, and you know all you do is put the obstacles and then find the shortest path from the top left to the bottom right. That's it. So you know, if you've been able to do some of the previous problems and have enough code, you can definitely do this one. This is just, you know, BFS from the very top left to the bottom right. You don't even need to do something like UCS because every edge cost is just 1. So for part 1, it was literally just, you know, by the way, first of all, let's make sure that we commit this. So like, you know, this is day 18 and push this to main so that we don't make any edits that we don't want afterwards. And yeah, so like, you know, this is the setting up the input and so on. By the way, one thing I did is I reversed every single X and Y coordinates because they give you, I'm used to like, you know, going down and then right first instead of going right and then down in terms of the coordinates. So I reversed them and so on, but that was just me. And so essentially once I parse the input, it's like, okay, I get the number of bytes that we want to consider. So it's like, you know, 12 if it's the test data, 1024 if it's this, because here they tell you like, you know, what are the first, what is the minimum, the shortest cost path if you only consider the first 1024 bytes. So it's like, you know, that's why it's 1024, otherwise 12 for the test case, because that's what they tell you. Here, this is just for the size of the grid, right? So like the goal state is 66 or 7070, depending on if you're doing the test case or not. So here I just have a global state variable that's called use test data. And so it's like, you know, I make it different whether I'm doing the test or the not test, right? And then it's otherwise, in terms of the actual problem, it's like, okay, my obstacles is literally going to be like, okay, grab all the lines that we have and their XY coordinates, go up to number of bytes, many of them, and put them all in a set, right? And that way we have a set of all the obstacle positions. And then we have, you know, a little function is obstacle and is bound. And so like inbounds is obviously like, you know, the X and Y coordinate, fill it in within that n value. And otherwise for is obstacles, it's literally like, you know, return, if given an X and Y, return to me that whether the X and Y pair is literally inside of that set of obstacles that we just defined, right? Otherwise it's just the typical, like, you know, here's the right, down, left, up directions. We set up our fringe, which in this case is, you know, a double-ended queue just because we're doing BFS, just because it's like here we want the shortest cost path. And when all edges are the same, you can use BFS. The only other case you can use BFS is like when the edges are like 0, 1, where I think it's like you can add to the left with the zeros and add to the right with for the 1 edges and so on. And that way you can still use BFS. But otherwise, you know, if all the edges are the same, you can definitely use BFS. Otherwise, you could use UCS. It doesn't really matter. UCS is essentially BFS, but using a priority queue. And the only one you can't do is DFS, right? Because obviously you'll just, you'll find a path, but not necessarily the shortest cost path. And then it's like, okay, while length of fringe is greater than 0, while we still have like, you know, items to visit, essentially it's like we keep popping these things. So here I just have my cost X and Y. It's like, okay, if my X and Y isn't visited, then obviously I don't want to do it again. Otherwise, you know, add that to my visit set. If we're the goal state, i.e. 7070 or 66, then it's like, okay, we found the optimal answer, printed and exit the program. Otherwise, it's like for each every single neighbor, if that neighbor is inbounds, it's not been visited, and it's not an obstacle because we can't go through obstacles, those falling bytes, that's like, okay, append that to my queue to be visited later on, and we're just going to keep going through this over and over and over until we either exit because we hit the goal node or we throw this exception. Obviously in this problem there's supposed to be a path from the top left to the bottom right, so we'll hit this case, and then when we run Python 3 part1.py, we hit it like a charm. We get 408, which is the exact answer, bada bing, bada boom, right? And for part 2, essentially what it tells you is like, okay, if you keep adding, you know, let's say the case where you add only the first byte, or the case where you add only the first 2 bytes, 3 bytes, 4 bytes, and so on, at some point, if you had enough bytes, the path to the goal node will be blocked, right? And so essentially you want to return, you know, what is the index of like, you know, the byte that once you add that alongside all the previous ones will cause, you know, everything essentially to for the path from the start to the end node to be blocked, right? Essentially the start is like the top left and the end is the bottom right, right? And so literally all I did is I literally said, let's just do leftmost binary search, right? So for part 2, literally all I'm doing is just leftmost binary search. And so all I say is like, hey, what is the minimum number of bytes I can have is 0. And of course, there will definitely be a path from the start to the end because there's literally no obstacles, right? You can just go through the entire top edge and the entire right edge. That's one solution. Otherwise, you can, you know, include all of the bytes, right? And if you include all the bytes, then there's, in this problem, there'll be no path and so on. So it's like, okay, between having 0 bytes, when I have 0 bytes, I have a path, right? When I have all the bytes, I don't have a path, right? So it's like somewhere along these lines over here, you know, somewhere in here, somewhere here, somewhere between these two values where it's like none of the bytes, all of the bytes, i.e. none of the obstacles, all of the obstacles, somewhere in this range, there's like an inflection point where it's like, here's like, you know, there's still a path, there's still a path, there's still a path, there's still a path. Oh, there's no more path, 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 right? So you can essentially think of these as Boolean values, right? So true, there's still a path, 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 boom. Inflection point, once you add this byte, there's no longer a path. And obviously any byte that you add afterwards will also mean that there's no path because the path is already blocked. You're only adding more obstacles. So if the path is blocked and you're adding more obstacles, the path will still be blocked. So it's like, you know, at some point it'll be false and there you go, right? And so essentially it's like, okay, you have a bunch of truths followed by a bunch of falses. And what do you want? You essentially want that very first false, right? And that's literally all I do. Here it's like, you know, I have a function that, you know, maybe I do check path exists and it takes a number of bytes. Here maybe I should have done, you know, like it should take an index, right? And so here's like I go up to that index and inclusive, right? And here's like, you know, this will be length of lines -1, and here this will be 0, whatever. We know, okay. And so here's like num bytes needed is equal to r. And then here it's like, you know, I could have done index. For part 2, I'll still get 4516, right? And so essentially here is like, you know, I'll do rightmost, leftmost binary search, right? Where it's like, you know, given an index, I want to find, you know, kind of like that leftmost false value, right? So it's like, you know, I essentially have a sorted array where it's like, you know, essentially it's like, you know, at index 0, it'll be like, you know, true there is a path, 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 right? And at some point, it'll be true there is a path, false there is no path. Once you add this guy, there's no more path from the start to the finish. Obviously, as you keep adding obstacles, it'll be false, 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 etc., right? And so essentially, this is a reverse sorted array, right? If you think of these as ones and zeros, you have a bunch of ones followed by a bunch of zeros. It's in sorted decreasing order, right? And so whenever you have a sorted array, you can, of course, apply binary search, right? And so here's like, okay, I essentially want to find the leftmost false because, you know, that is the first byte that if I added would make, you know, the path from the start to the end blocked, where essentially here I have a function where I took the function from part 1 to essentially, you know, find the minimal cost path. But instead of returning the cost of the path here, I just return true whenever I reach a goal state because, you know, that means I found a path. Otherwise, if I've exhausted the full fringe, you know, of the full queue, and I still haven't hit a goal state, that means there is no path, and so I just return false, right? So I just made that small modification in part 1. So returning the cost, return true or false whether there was a path. And then it's like, you know, I just like, you know, leftmost binary search, you know, 0 and the last index are, you know, the two extremes where it'll be definitely true on one side, definitely false on one side. And then it's like, okay, keep going to the middle. And that way it's like, you know, if I hit a true, then it's like, okay, obviously I'm not interested and I need to keep looking in the right sub half, right? If I hit like, you know, a false, then it's like, okay, mark that as a potential solution and look in the left sub half to see if there's even earlier falses, right? And just keep doing that over and over and over, right? So it's just leftmost binary search. Two extremes over here, and it's like, okay, keep grading mid. If there is no path, right, then that means it's interesting to us. We want the very first byte that causes there to be no path. So we'll set index to, you know, the minimum between index and mid, although we don't even need to do a minimum. We can just do index is equal to mid because it'll always be set to a smaller value. So if I do this, it'll still be the same thing. It's just, this is me having paranoia right there. And then it's like, okay, once we have found a valid value, then it's like, okay, we essentially have found a false, right? So what do we want to do? We want to check in the left sub half to see if there's even earlier falses, right? So that's why we said r is equal to mid minus 1. Otherwise, if we found a true, well, again, we want to find the leftmost false, right? Because a false essentially represents that there is no more path. So we want to find the very first index that essentially caused us to no longer have a possible path. So in this case, it's like, okay, we have a true. We want to look in the right sub half to find the very first false. So that's why we just do L equals mid plus 1 and don't update it in the index, right? Because here we found a true. We only care about the falses, right? And then once I'm done with this whole spiel and shenanigans, index will essentially be, you know, the leftmost, the index of the leftmost false, which essentially represents, you know, the index of the obstacle or byte that will cause the path to be blocked. So there I can just return that position, right? And here you'll notice that I do index 1 followed by index 0. And this is because, you know, as I said at the beginning, I essentially reverse all of these coordinates just to make my life easier because I'm not used to the way that these guys give it. They give it like, you know, they give the x-axis and then y-axis. I'm used to like, you know, y-axis and then x-axis. And so here it's just like, okay, I had to reverse it. But if you didn't reverse it for your input, you don't have to do this, right? This is just something that I had to do. And yeah, so hopefully that solution made sense. I'm trying to make my solutions a bit more succinct, you know, where it's like, you know, I don't go like, you know, too crazy over the detail and so on. That way it's like, you know, if you just want a short summary of what I did, I'm trying to make them, you know, a little bit shorter. So it's like, okay, that's you know, neat what this guy did, instead of like, you know, a super in-depth 1.5 hour analysis that no one is going to watch. So, you know, hopefully that solution made sense. And yeah, but otherwise, that is pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.